we'll get started today. Okay, so I wanted to talk about the midterm exam. Oh, so reminder again, I have to cancel class on Friday. I've got kind of this all-day faculty meeting with the statistics department, and so I have to go there. So we won't have class on Friday. And I know the midterm was originally scheduled for Friday, but I'm moving it to we're moving it to Monday. So it'll be Monday, November 8th. It'll be right here. You know what? I might send out a seating chart, okay, just to kind of get everybody to be spaced out. I know that's a little bit weird, but we might do that, okay? All right, let me just talk a little bit about what you can expect for the midterm exam, okay? So as far as the midterm exam, I will provide a few pages, okay? I will provide, as part of the exam, you will get, so if you go to the RStudio cheat sheet website, okay, there is a cheat sheet for ggplot, a cheat sheet for dplyr. There's a bunch of cheat sheets, and they're all really, really, really good. There's a bunch of stuff that we haven't even talked about, but they're all really excellent. But I will include these two cheat sheets, the ggplot and the dplyr. These are probably your two most important packages as far as the tidyverse goes, in my opinion. Of course, all of the other packages that are part of the tidyverse are excellent. But I would say ggplot, dplyr, those two cheat sheets will be included, okay? You'll also get your standard normal table and the t table, which I guess is back here. Okay, the reference tables here. Those, at least the normal table and the t table from there will be included. Okay, so that's 4 pages of reference material. You are also allowed 2 sheets of notes. All right, so whatever notes you want to bring to the exam, that's fine. 2 sheets of notes, front and back. Okay, so I guess 4 sides total, 4 pages. Two. Does this make sense? 2 sheets, front and back. Okay, I don't want to have to be like, I don't want to take away somebody's notes or something because they didn't understand that it's just 2 sheets, front and back or something. Okay, and letter size, none of this giant sheet of paper getting away on some technicality. Yeah, question. Yeah, it can be typed, handwritten, whatever you want. Okay, I'm not very particular about that. All right. I would prefer if you make your own, although, like, I don't know how I'm gonna, like, if someone comes up with a really awesome note sheet and prints it off, I mean, I don't know how I'm gonna stop it, but just, I think you're better off making your own things, okay? All right, so pretty much all the content from weeks 1 through 6 could make an appearance, with the exception of kind of week 3, lecture 2, and ethics. It's like hard to write an exam on ethics without it turning into like some essay question, and I don't want to have you guys write an in-class essay, and I don't want to grade an in-class essay. So I won't ask any questions about ethics. Not to say that that's not important, okay? Just because I'm not testing you on it doesn't mean it's not an important topic, okay? But I don't feel like grading an ethics question or an essay. So we're not going to put, you won't see ethics questions, and you won't see, there's one lecture where we did like nesting and RVest, like scraping the web and reading in data. That we won't include stuff from there, okay? But pretty much the other stuff, ggplot, dplyr, your group by, your summarize, your mutates, and tidyr, where you pivot longer, pivot wider. So those could make an appearance, okay? And as far as what will those questions even look like, I'm still kind of writing these questions, and again, the great challenge for me as the teacher is figuring out how hard to make these questions and how many questions can I include in basically a 45-minute time period, okay? Because our class session is 50 minutes, and I like to just have a couple minutes at the beginning and end to kind of collect and pass things out. So planning for 45 minutes, I got to think, how many questions can I ask and how hard can these things be? And obviously, I'm not a good judge for how long things take you guys, right? So it's always kind of, how long it takes me is probably 3 to 4 times faster than you guys. But that's just because I've been doing this for a long time. Yeah.
So will this be like on paper? Will it be like?
Yeah, it's going to be paper, right? So it's going to be pen and paper. And so anyway, the code questions, I think the best format, well, if you go back to kind of like the data camp homework that I've been assigning, okay, you click a thing and there will be, a lot of times it will give you a prompt and there will be some code started off but with kind of some blanks, or just maybe you'll have a comment that says, write this thing, right? And usually you have to write maybe like 2 lines of code total, or fill in the blanks or something like that, okay? And it'll probably be something like that, where I'll have a couple lines. I'll say, this is kind of the scenario, write the command that's going to kind of complete this, okay? So I would say, as far as studying, see how much you can get through, on data camp without running into errors or things like that. And, expect the challenge to be kind of like that. Maybe some exercises are tougher than others, and probably it will fall slightly on the tougher side of the data camp exercises, if that makes sense, as far as coding exercises. And it's gonna, and the other hard part is it's all gonna be handwritten, right? So you'll have kind of the lines of code written on the piece of paper, and then you'll have to either write in by hand the missing kind of values or variables or arguments or function names, or you might have to write an entire line or two on your own as well, okay? And that's kind of what you can expect for these exercises. And I think I've assigned, as far as the homework goes from data camp, I think I've assigned a good selection of chapters that cover a lot of these different topics there, okay? And then you'll have some kind of a mix of traditional stats class questions, where I'll have questions based on the normal distribution, based on sampling distributions, based on questions about confidence intervals and the t-test. And I would say those types of questions, you can the homework that we've assigned this week, homework 4, that come from the textbook, the AP Stats textbook, you can kind of expect them to be somewhat similar there. And those questions will be formatted to be kind of short numerical answer. So it'll just kind of ask you a question, and then you'll just write your numeric response there. Okay, yeah, question? You can use a calculator, all right? You can use a calculator, that's fine. Any calculator is fine, just not your phone or a tablet, okay? Or don't say, I'm using my computer as a calculator. Technically, your computer can work as a calculator, but just, something that doesn't talk to the internet, right? So that's fine. But yeah, obviously, because, you got to do some division, and a calculator will be handy for that. So that's fine. Yeah. Yes.
What model grade the curve?
Well, I don't curve grades. I don't believe in curving. So there's different philosophies as far as grading goes, and curving inherently compares you versus your peers. And so if your peers do poorly, then that benefits you. But if your peers do well, it harms you as far as curving goes, because it says, the top this percent get an A, and the next get a B, and the next get a C. And I don't think that's right. I think you should just be tested against the material, And it's really up to me to write a good exam. Now, if for whatever reason, right, I write this exam, I give it to you guys, and everybody does like totally crap, right? So I'll just tell you, my ideal scenario, ideal distribution for grades is the median would be in the 80s. So the ideal would be a median of 85. If it's lower than that, that's okay. If it's higher than that, that's also okay. If the median drops below, say, I would say 78 or something like that, right? If the median is 78 or lower, then I would say, okay, maybe I made my exam a little bit too hard. And in those cases, what I do is I usually just add points across the board. So if the median was, say, 78, I'll probably just add 7 points to everybody's score straight across the board so that the median becomes an 85, right? And so that means if somebody got 100, their score becomes a 107. And if somebody scored a 30, their score becomes a 37, okay? But usually that doesn't happen. Not to be completely arrogant about the situation, but I feel like I'm able to write fairly decent exams. And again, this is the first time I'm teaching this course, so there's going to be some learning for me. But my hope is to write a 45-minute exam where the median will be 85, and I'm hoping the third quartile will be in the 90s, and the first quartile will be, 75 or something like that. Okay? Yeah. Yes.
How much percent of our total grade will this midterm be?
You know what? I better check the syllabus there, because it pretty much that's answered in the syllabus, but I don't remember all of these things off the top of my head either. So syllabus says grade breakdown 16%. Oh, that's hardly anything. Your lecture review quizzes are worth almost just as much as your midterm exam. So I must have been in a very generous mood here when coming up with the grade breakdown. Okay? I think that this is very generous. All right. Oh, you guys better start racking up those campus water points, though. That's 4%. Just upvote everybody else's answers, okay? There's nothing stopping you from doing that. It doesn't cost you anything. Just answer each other's questions and upvote each other's answers. Okay, questions on what the midterm will look like? So I don't know exactly how many questions it will be. I'm still kind of playing around with that, and I'm still trying to figure out the exact timing on that. But yeah, okay. Okay, well, so that will be Monday, all right? And so again, I'm not going to see you between now and Monday. So but I'll send you some emails. I will probably email out like a seating chart that says, come sit here. And it just kind of helps make sure everybody's spaced out. Just because there have been incidents in the past where, friends sat together and then their answers looked the same, and it was an issue. And so it only takes a couple students to make things so much more complicated. Okay, all right. So the last thing. So in today's lecture, we're going to cover t-tests, the hypothesis test for a mean, and this will kind of, again, I'm doing this. I don't even know if the task of trying to compress what I believe to be the essentials of, say, like an AP statistics course or your introductory stats 10 course down into kind of 2 weeks. So there's a lot of stuff we kind of skipped out, and there's a lot of stuff that we're not going to get to, but to kind of compress those concepts down into 2 weeks, that's what we've been trying to do between last week and this week. And so pretty much we've been focusing on the normal distribution, and then we started talking about sampling distributions, and then we did inference based on these sampling distributions. So we covered confidence intervals, and now we're going to cover hypothesis tests. Okay, and then once we do this, we'll return kind of back to our textbook. After you take the midterm exam, we'll return back to the textbook, and we'll get back into kind of using R and thinking about our data to perform statistical inference and modeling, which is what you will need to do as far as your final projects go. Okay, you'll do descriptive statistics and data visualization, which we've kind of covered, and then you will do some modeling and predictions and things like that. Oh, thank you guys, the rest of you, for your flexibility in rescheduling things. You know, after meeting with the first two groups, I realized I have a lot to say when meeting with these, when meeting with the groups during the proposals, and so I wanted to make sure I had enough time to kind of to get through. And and also when you meet with me for the data proposals, I see kind of my job during the data proposal as to be this very I don't want you to get the wrong impression about these meetings. I'm there to be very kind of critical about just is this data good? What are some potential problems with this data, right? So I don't come in with these rosy glasses, and I don't want you to be discouraged if I ask you a bunch of questions about or if I suggest that there could be potential problems with the data. Okay, sometimes students get discouraged when I say, I think this problem or this variable could be an issue, and they feel like they almost need to abandon that data set. And that's probably not the case. It's just you really need to be aware of a lot of these issues. Okay, if you just take data coming in and you assume that it's golden and good data, that could lead to a lot of problems. But if you're aware, if you get the data coming in here, if you're aware of certain issues and you say, all right, I can't use this as well as I would like, you can still use that data, but you just have to kind of qualify all of the conclusions that you're making. And I think that's more important, rather than just kind of throwing everything out and saying we can't deal with anything, but also saying, but not just assuming everything is 100% accurate. There's kind of a balance that we've got to walk. But yeah, these project proposal meetings, I might come across as a little bit harsh, but it's nothing nothing personal. Okay, so just be prepared for that when you guys meet with me. Okay, let's talk about hypothesis tests, and we're going to be doing a hypothesis test for a sample. And what we're trying to do is we're trying to make conclusions about the population based on the sample or samples of data. And so far we've talked about the confidence interval, and the premise of the confidence interval was, according to the sampling distribution, our x bars are close to the mean mu, and therefore if we see a particular value for x bar, we can be confident that mu is nearby. Okay, the hypothesis test is another tool of statistical inference, and is kind of a bit of a framework. Now, and here we're just looking at one very, very, very basic hypothesis test, the t-test. And technically there are probably a dozen, 100 different types of hypothesis tests out there, each for a different kind of sample statistic, each for different things that we could ask and test. And they all kind of follow a similar framework, but here we're just starting off with just kind of this very basic one, okay? And so when we do hypothesis testing, we pose our research question, whatever we're asking, it has to be stated as some kind of testable hypothesis. And we call this thing the null hypothesis. And what we do is we test that hypothesis against the data that we've observed. So in order for a hypothesis to be testable, it has to be a specific claim. If it makes a vague claim, you can't test it, right? Just like if you were to see a fortune teller and they were to say, oh, you will encounter an interesting person in the coming days, that is so vague that it can neither be proven nor disproven, right? Because of course, at some point in the future, you will meet an interesting person, and you know, if you're prone to believe this fortune teller, then you might say, ah, yes, this proves it, but it's also just, again, so vague that it can neither be proven or disproven. But if you make some kind of very specific claim that says, you know, on November 10th, you will meet somebody who, I don't know, works for this company, or, you know, is in this line of profession, you know, the more specific it is, then we can test that and see, okay, did that thing actually happen or not? And if it does, then that you would be, you know, surprised and impressed by the abilities of said fortune teller. So anyway, as far as the t-test goes, with one sample, we're going to say the population, the claim that we are making about the population is that the population has a mean mu, and this mean mu is exactly equal to some value m. This is the claim that we are making. It's a very specific claim. We are saying that the mean of the population is exactly equal to this value m, okay, or whatever letter you want to pick. Okay, and so how do we test this? Oh, you know what? I always get too excited about topic. First view quiz answer for today is the letter E. E as in elephant. E as in elephant. First view quiz answer today. So what we do when we test the hypothesis is we say, let's assume that the claim made by this null hypothesis is true, okay? Remember, the null hypothesis says the population has this mean mu and it's exactly equal to m. And so we say if the population does have mean equal to m, if the population has mean equal to m, then when we select random samples drawn from the population, we would expect these samples to have sample means that are equal to m, or at least fairly close to equal to m, right? So if we claim m is 7.0, then we expect our samples to be pretty close to 7, to have means close to 7.0, 7.1, 7.2, I don't know, some number, right? That's what we're expecting. When we look at our data, our sample has a mean x bar, okay? And this x bar perhaps probably is not going to be exactly equal to m. It's different by x bar minus m. The difference between my sample and what this hypothesis claims is x bar minus m. Let's say that difference is 0.5. Okay, and the question is this difference, 0.5, is this a big deal or not? Okay, if the null hypothesis were true, we expect that difference to be 0 or close to 0. We're getting a difference of 0.5, and the question is 0.5 significantly different from 0? That's what we want to know. Okay, so how do we answer that, right? So, you know, we continue and we say, well, I know samples are subject to randomness, right? If I take a random sample, maybe I get something where the mean is, 0.5 more than what the population claims to be. Somebody else could get a random sample and maybe it's 0.3 less, okay? And so we ask, if the population does have mean equal to m, what's the probability that randomness alone could produce a difference of x bar minus m, or 0.5, okay? And so we got to do some calculation. Then we're going to answer this question. What's the probability that randomness alone could produce a difference of x bar minus m equal to 0.5 or more, okay, something more unusual, if the null hypothesis were true? And the answer to that is what we call a p-value. A p-value is the probability of getting what we have observed in our sample for something more unusual. All right, so here's our definition. The probability, p-value, is the probability of observing a statistic in our data or something more unusual if we assume that the null hypothesis were true. And in the context of our problem, the p-value is the probability of observing a difference of x bar minus m 0.5 if the population has a mean equal to m. And so we can go through and we do our calculations, and there's a few possible outcomes. One is you go through the calculations and you say, hey, if the population has mean m, what's the probability you get a mean of x bar that ends up being 0.5 more than m? Okay. Maybe that result says it's unlikely to be observed, right? So population, we say population has a mean of, I don't know, 8. And you take random samples most of the time, right? So we could do a sampling distribution, right? The population has a mean of 8. We take different samples. Our samples, sometimes we get a mean of 8.1, 8.2, maybe 7.9, 7.8. How often do we ever get a sample where the mean is 8.5? And maybe the answer is no. Maybe it happens like once every 10,000 samples, okay? Most of our samples have means of 8.1 or 8.2. And only very, very, very rarely do we get 8.3, and almost never do we get 8.5. And so the fact that we got 8.5, right? So again, this is if the hypothetical situation were true, right? If our hypothesis claim that the mean of the population is 8, and we kind of simulate that, and we say, well, how often, if that were the case, what's the probability that a population centered at 8 could produce values of 8.5? And it turns out it's very small. The p-value is very small. So the fact that we did get this value of 8.5, right? We get a difference of 0.5, which is said to be unlikely. This actually tells us that we're not living in this hypothetical world centered at 8.0. We're probably living in a world where the mean is a little bit higher than 8, maybe 8.4, and that's why I'm getting a value of 8.5, okay? So the fact that we get this difference, which is said to be unlikely, provides evidence that the claim made by the null hypothesis is wrong. And we conclude the reason why we see a difference of 0.5 in our sample is that the mean of the population is not equal to m, but is equal to something a little bit higher, something closer to the value of our sample mean, rather than whatever value m is claiming to be. Okay. Does that kind of make sense? The logic here, yeah.
Are we going to use like an alpha?
Yes. We will use an alpha, and we'll talk about that. Okay. On the other hand, you do your calculations. The p-value ends up being large, right? You go through your calculations, and it says, yeah, if the population, there's a typo here. If the population mean is equal to m, a difference of 0.5, it's not that weird, okay? It's not unlikely to happen. And so the fact that we got this, right? The null states that the mean mu equals m. We expect our samples to have x bar minus m to be close to 0. We're getting a difference of 0.5. That's more than 0. But it says, hey, that's not that weird, right? If the population is centered at 8, sometimes you get 8.1, sometimes you get 8.2, sometimes you get 8.5, sometimes you get 8.7. It's not that weird to get 8.5, right? So you're getting a difference of 0.5, not that weird. And so we would say we don't have a reason to believe that mu is different from m, okay? It doesn't prove that mu is equal to m. It just says we don't have evidence against this claim right now, okay? So we're going to say we don't reject the claim made by the null hypothesis. So whether we decide if the p-value is large or if the p-value is small is determined by our significance level alpha. So we pick an arbitrary value, alpha. We call this our significance level. And it's just a arbitrary line. And we just say, hey, if the p-value ends up less than alpha, that means it's small. And if the p-value is bigger than alpha, then that means it's big, right? It's kind of like you must be this tall to ride at, you go to Six Flags Magic Mountain or something. I don't know if you guys go to amusement parks, but it's when you're in like 5th grade, you're like, oh, am I tall enough to go on the roller coaster? And it's just basically an arbitrary line that the manufacturers of the roller coaster said, hey, you got to be this tall to ride, and if you're shorter than that, you're too small to ride. If you're taller than that, you're big enough to ride, okay? And so here we're just saying if the p-value is less than alpha, it's small, and this means we're going to reject the null hypothesis that this is said to be unusual. Our data leads us to reject the null hypothesis. And if the p-value is greater than alpha, then this means the p-value is considered to be large. And that just means even if the null hypothesis were true, our data is not an unusual result. We would not reject the null hypothesis. Okay? This choice of alpha, the significance level, is arbitrary. A very common choice is, say, alpha equal to 0.05. You can also use alpha 1%. Sometimes you could use alpha 10%, but I'd say that's a lot less common. Usually the biggest alpha you'll see is something around 5%. But you could use, it's not uncommon to use smaller alphas as well. Okay, and again, these are just arbitrary lines that statisticians that kind of it's been established that we like 5% for whatever reason. It probably should be something around 5%, but is there anything magical about the number 5%? No, there's nothing magical about it, right? It's kind of just like you are considered an adult when you turn 18, right? Is there something magical that happens on your 18th birthday? No, there's nothing magical that happens. But at that point we say, you're now responsible for every decision yourself, right? You want to take out student loans, now you're responsible, right? You want to join the military or buy a gun. We say, you're 18, you can do it, right? There's nothing magical that happens, but this is just kind of the line that we've agreed to as society, and we go off of that. And so kind of in a lot of research journals, 5% is kind of the threshold that happens, and it's probably okay, but there's pitfalls to it as well. Living and dying by the p-value alone is probably a bad idea, just because it's not nuanced at all. Okay, so one important thing is that when we make a hypothesis, it's always a statement about the population. You never write a hypothesis about your sample. You're never going to write, in the null hypothesis, I'm saying that the sample mean is 7.5. Okay? That would be a silly thing to say, because the whole point of the hypothesis test is we're trying to make a conclusion about the population. And what kind of conclusions can you make from your sample? Your sample is right there. You can observe it directly. So you can get the mean of your sample. It's silly to say, I'm proposing that the mean of my sample is 7.5. It's either 7.5 or it's not, right? You can observe it directly. What we're trying to do is we're trying to make hypotheses about the population, which we cannot observe directly, and that's why we're bothering with a hypothesis test in the first place. Okay, let me give you your second view quiz answer. Second view quiz answer today is D. D as in dog. D as in dog is your second view quiz answer. All right, so the null hypothesis is the hypothesis or claim that we are testing. The null hypothesis will always have an equal sign. And then the null hypothesis is paired up with an alternative hypothesis. The alternative hypothesis is can be non-directional, which we might call a two-sided test, or they can be directional, which we would call a one-sided test. And whether or not you use a directional or non-directional depends on the question. Okay? So for the t-test, the null hypothesis is mu is equal to some value m. We're making the claim that the population has mean equal to m. If we're interested in the possibility that the means are different, we would use a non-directional, that the mean is different from m. We would use a non-directional alternative. We would use mu is not equal to m. We'd be interested if mu is larger or smaller than m. In some situations, you're only interested in one side. And in that case, you would use a directional alternative. So you could use mu is greater than m, or mu is less than m. And so here's a silly example. All right, so let's say a company is developing a product to lower blood pressure or something, and let's say our current average, I don't know, is 120. okay? I'm just making this up, okay? And we're interested if the product helps reduce blood pressure. So our null hypothesis is that the drug does not affect blood pressure, that the mean remains the same at 120. And the alternative is that people using the drug have lower blood pressures. It's now less than 120, okay? If the data ends up being X bar greater than 120, that means the mean blood pressure of people using the drug is higher than 120, okay? Then there's no point in continuing our analysis. The goal was to see if it can bring people down below 120, right? And if the data ends up showing if your X bar ends up being greater than 120, what's the point, right? We're not going to bother with this thing, right? So we can, at that point, you can just conclude that you simply don't have evidence supporting the idea that the drug is effective at lowering blood pressure. You're only interested, as far as the drug company is concerned, they're only interested if it's successful at kind of lowering this number, and if something else happens where it actually goes higher, then we don't want that. Okay, so we would have a one-directional thing. Okay, so silly example hypothesis test. So forgive the example here. Is the average length of a banana? How long is a banana? Right, you go to the grocery store, you buy a banana. Yeah, how long is it? I don't know, right? We're going to just say, hey, is it 7.5 inches? I don't know. Okay. So somehow, and I don't even know how this could even be possible in real life, but we're going to pretend that we got a truly random sample of 20 bananas. So maybe we went to a banana farm and we picked out 20 different trees and we just picked one banana off the thing. I don't know, right? But anyway, we measured the lengths of these 20 bananas. And the mean is 7.0 inches. So our sample is 7.0, and we're testing this against the claim that the population is 7.5. All right? Standard deviation 0.7 inches, and so we say, does our data provide evidence that the average length of a banana is not 7.5 inches? I don't know. All right, so this is what we want to know, okay? So we're going to create our hypotheses, right? Again, we're dealing with means. Our symbols on the hypotheses will be mu. Don't use X bar. The null hypothesis will be that the average length of a banana is 7.5 inches, because that's what the question is. Does your data provide evidence that the average length of a banana is not 7.5 inches? So the null hypothesis is that it is 7.5, and the alternative is going to be just not equal to 7.5. Because here we're not just asking, hey, is the mean going to end up? It didn't say is the average length of a banana less than 7.5, right? If we're only testing one direction, we would use a less than sign. Okay, so we got mu equals 7.5, mu not equal to 7.5, right? So we check and we use our significance level. The default is 5%. We have to check a few conditions, right? So is our sample random and independent, right? So we're going to assume this condition's met. We're assuming we have a random sample. Is the sample large enough? Okay, maybe, right? If the distribution of bananas is somewhat unimodal symmetric, a sample size of 20 is probably big enough. Kind of rule of thumb is 25 or more is going to be big enough in most situations. Sample size of 20, probably big enough. But it's also possible that banana lengths are like really skewed and a sample size of 20 is not big enough. But we're going to assume that this condition is met, okay? Big population would be all bananas. This is a big population. We can do that, right? So we're going to ask, what's the probability of getting our data or something more unusual if the null hypothesis were true? So our data is that we have a sample size of 20. Our mean is 7.0. We have a standard deviation of 0.7. And if the null hypothesis were true, mu is equal to 7.5. And so we're asking, what's the probability of getting an X bar of 7.0 or less, or X bar of 8.0 or more? Because our difference between what we've observed, 7.0, and what was hypothesized, 7.5, that's 0.5, and we're asking what's the probability we get a difference of 0.5 or something even more if the null hypothesis were true. So according to the central limit theorem, we can say, hey, the sample means x bar come from a normal distribution. The mean is going to be equal to 7.5, which is what the null hypothesis states. So if the null hypothesis were true, this is the case. And our standard error would be 0.7 divided by the square root of n. Okay? And this is what we have here. Okay. So if that's the case, then we would calculate our z-score. We would say, okay, how different is x bar from the mean divided by the standard error? 7.0 minus 7.5 divided by 0.1565. We're getting a z-score, not a z-score, I guess it's the t distribution. So we're getting a value of negative 3.19. Negative 3.19. When we use the t distribution, we use n minus 1 degrees of freedom. So we're going to use 19 degrees of freedom. Okay. N minus 1 degrees of freedom. So what we do is we go to our t table. So if you click the reference tables, and this packet is 6 pages long, but I'm just going to give you table 2, the standard normal. I'm going to skip this binomial probability table, and I'll give you table 4, the t distribution. Okay, so if you go to the t distribution table, we're going to go to the row 19 degrees of freedom here, right? And I copied and pasted that here. And what we want to do is we want to look for where 3.19, which is our value, right? We got negative 3.19. We want to see where 3.19 fits, okay? Now our value is negative, but the t distribution is symmetric, so we can kind of ignore it and just look for it. So we're just looking for 3.19. We say 3.19 is in between these two values. And the way it works is that if your t ended up being exactly 2.861, the amount in your tail, this right tail probability, would be 0.005. If your t is farther away at 3.579, the amount in your tail is even less, 0.001. Okay? If your t is exactly at 1.328, you would have 10% in your tail. So our t is at 3.19, which means we're farther away than 2.861, but closer than 3.579, which means the amount in our tail is going to be less than 0.005, but more than 0.001. We don't have an exact value, but we know it's got to be less than 0.005 and more than 0.001. Okay, so that's what we're going to say. We're going to say our tail area is between these two numbers. Okay. Our alternative hypothesis is a two-sided test, so we're going to take these numbers and multiply it by 2. So if I multiply 0.005 by 2, I get 1%. If I multiply this by 2, I get basically 2 thousandths, 0.002. So my p-value is somewhere between 0.01 and 0.002, something really small, less than 1%. And so what do I do? Well, if our significance level is 5%, the p-value that I have, something which is some number, again, I don't have the exact number, but it's some number between 1% and 0.002, this p-value would be considered small. And so technically, it's not impossible to get a sample mean of 7.0 inches. If the mean length of a banana truly is 7.5 inches, it is still technically, theoretically possible to get a mean of 7.0 inches, but what we're saying is that this is unlikely to happen. It happens less than 1% of the time. So the fact that it did happen, that we did get this sample of bananas where the mean is 7.0 inches, we could either say I was one of the lucky less than 1% of people who get this kind of bizarre looking sample, or rather this claim that we originally made that the mean length is 7.5, that original claim is wrong. Okay? And what we're going to do is we're going to just end up concluding that the mean banana length is some other value. Some other value, probably not 7.5, maybe 7, something smaller, 7.1, 7.2, something less than 7.5. And that's why I'm getting a mean of 7.0. The reason why I'm getting 7.0 is not that I was the lucky 1% who get these really unusual samples with really small values, but just actually the population mean probably is closer to 7.0, and that's why I ended up getting this sample, right? And so that would be the conclusion that we make. All right. Is this whole process okay? All right, so that's basically the t-test. That's a hypothesis test. And this is this wraps up kind of our whirlwind 2-week compressed version of what I deem to be kind of the essentials of statistical inference, okay? And so hopefully that gives you a little bit of a base for us to work with as we move forward in the course. So you can expect some questions about, statistical foundations and stuff on the midterm exam, and basically what I've written out in that midterm description, you can use that as a study guide. Yes, question.
Are we only going to do significance test for means?
Yeah, just for means, okay? Just that's as far as we'll get as far as these classical tests. Now we can probably what I'll do is we'll look at like randomization tests, which can be kind of generalized to kind of any kind of statistic as well. Oh, your third view quiz is the letter B. B as in bear. B as in bear is your third view quiz answer today. Okay, we'll end here for today. Have a good day. I will not see you on Friday, so enjoy Friday. You can sleep in a little bit, I guess, and then we will see you guys on Monday. All right, and good luck as you study, and we'll see you guys then. Okay. Well, I guess some of you I'll see before because we're gonna have meetings, so some of you I'll see before, but if not, I'll see you guys on Monday.